Hello everyone, today we start chapter 9, Counting and Probability. I start this chapter by the definition of probability and sample space. We say the sample space is a set of all possible outcomes of a random process or experiment. What is a random experiment? It's an experiment with random outcomes. An experiment that we don't know what the outcome is for sure. For example, when you toss a coin, you don't know if you see a head or a tail. That's why tossing a coin is a random experiment, and a set of seeing a head and seeing a tail is the sample space for this random experiment, because it is all possible outcomes of tossing a coin. And then we define an event as a subset of a sample space. So for example, seeing a head is an event, seeing a tail is another event. And then here we define the probability in a simple way. We say if S is a finite sample space, so it means S represents the set of all possible outcomes of a random experiment, in which all outcomes are equally likely, and E is an event in S, it means that E is a subset of S, then the probability of E, which is denoted by this symbol P of E, is equal to this ratio, the number of outcomes in E divided by the total number of outcomes in S. So it's equal to the cardinality of E to the cardinality of S. We show the cardinality of E with n of E, and we show the cardinality of S with n of S. So basically, this ratio represents the probability of event E. In the example of tossing a coin, if we want to find the probability of seeing a head, then the number of elements in the event E is 1, because we only want to see one element, which is seeing a head, right? And then n of S, which is the total number of outcomes of this experiment, is 2, because we can either see a head or a tail. So the probability of seeing a head becomes 1 divided by 2, which is 50%, or 0.5. Okay, so now let's see an example of the book. Example 911, probabilities for a deck of cards. An ordinary deck of cards contains 52 cards divided into 4 suits, right? The red suits are diamonds and hearts, and the black suits are clubs and spades. And then each suit contains 13 cards of the following denominations: 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. The cards Jack, Queen, and King are called face cards, correct? And then imagine that the cards in a deck have become so thoroughly mixed up that if you spread them out face down and pick one at random, you are as likely to get any one card as any other, right? So the chance of having like 2 of diamond is equal to the chance of having 4 of spade, or 5 of king, 5 of clubs, right? So the chance of having any card is the same as any other. Okay, so the question here is, what is the sample space of outcomes? Since we have 52 cards and we are choosing one of them in random, then the outcome of the sample space S are 52 cards in the deck, right? So for each card in the deck, we have one outcome. Since we have 52 cards, then the sample space has 52 different elements. Then what is the event that the chosen card is a black face card? Such event has 6 different possibilities. The first one is Jack of club, then Queen of club, then King of club, then Jack of spade, Queen of spade, and King of spade. Why? Because we are interested in seeing black and face card. We have 2 suits, 2 black suits, and 3 face cards. So a combination of these is have 6 different possibilities. Jack of club, Queen of club, King of club, Jack of spade, Queen of spade, and King of spade. So in part 3, in the third part of the question, we are asked to find the probability that the chosen card is a black face card. So we are interested in finding the probability of event E that we represented here using a set roster notation. Since the number of elements in E is 6 and the total number of possible outcomes, which is the number of elements in the sample space, is 52, so according to the definition of probability, P of E is equal to N of E over N of S. We have 6 elements in E, 52 elements in S, so the answer is 6 divided by 52, which you can calculate it and compare and then convert it into a percentage representation, which becomes 11.5%. So the chance of seeing a black face card when choosing one card out of a deck is almost 11.5%. Okay, so as you saw in the definition of probability, in order to find the probability, we need to count the elements in a set. We need to be able to find the number of elements in the sample set and in a given event, right? So counting the element of a list helps a lot to find the probability of different events in different random experiments. That's why here we have a theorem for counting the number of elements in a list. Here is the theorem. It says if m and n are 2 integers such that m is less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. For example, if you are asked to find the number of elements between 1 and 100 inclusive, we know that there should be 100 elements, right? But you can also use this theorem to find the number of elements, the number of integers from 1 to 100 inclusive. You can say 100 minus 1 plus 1. So 100 minus 1 plus 1 becomes 100. So using this theorem, you can also prove that there are 100 numbers between 1 and 100 inclusive. As a little bit harder example, consider example 914 of the book, which asks us to find how many 3-digit integers are divisible by 5. So when we say 3-digit integers, we mean integers from 100 to 999 inclusive, correct? So by the definition of divisibility, we can conclude that there is a 1-to-1 correspondence between the 3-digit integers that are divisible by 5 and numbers 20 to 199 inclusive, the integers from 20 to 199 inclusive. In fact, if you multiply 20 by 5, you get 100, which is the smallest three-digit integer that is divisible by 5. Then 21 by 5 is equal to 105, which is the second three-digit integer that is divisible by 5. And it can go all the way to 199, which if you multiply it by 5, you get 995, which is the largest three-digit integer that is divisible by 5. So we can say there's a one-to-one correspondence between integers from 20 to 199 inclusive and then three-digit integers that are divisible by 5. So based on the theorem 911, we can say there are 199 minus 20 plus 1, which is 180 integers from 20 to 199. And since there is a one-to-one correspondence between these integers and all the three-digit integers that are divisible by 5, we can say the total number of three-digit integers that are divisible by 5 is also 180. And then in the part B of this example, we are asked to find the probability that a random chosen three-digit integer is divisible by 5. In order to find that, we just need to use the definition of probability. So in the definition of probability, we need to find the number of elements in the event, in the interested event, divided by the total number of possible events, which is the cardinality of the sample space. So first we calculate the cardinality of the sample space, which is the total possible number of ways that we can find a three-digit integer. So the three-digit integer is an integer from 100 to 999 inclusive. So we have a total of 999 minus 100 plus 1, which is 900 different three-digit integers. Here we use theorem 911 to find the cardinality of the samples set. Now, based on part A, we know that then we have 180 different three-digit integers that are divisible by 5. So here we have n of e equal to 180, and we calculated n of s, the cardinality of sample set, to be 900. So based on the definition of probability, we just need to calculate the ratio of 180 divided by 900, which is 1 divided by 5, or 20%. Okay, so in the next section, we talk about possibility trees and the multiplication rule. What is the multiplication rule? Consider the following example. Consider that a computer installation has 4 input and output units, A, B, C, and D, and 3 central processing units, X, Y, and Z, correct? Any input-output unit can be paired with any central processing unit. The question here is, how many ways are there to pair an input-output unit with a central processing unit in such computer? To answer this question, you have to first consider pairing of 2 types of units as a 2-step operation. In the first step, you have to first choose what kind of input-output unit you want, and then in the second step, you have to choose what kind of central processing unit you want. So in order to find the possible outcomes of this operation, we can draw a tree like this, This is the start point, and then we have 4 different ways for doing the first step. For choosing the input output unit, we can either choose A, B, C, or D, and then for each of these 4 steps, for each of these 4 possible input and output unit, we have 3 different units in the second step. So for example, if I choose A in the first step, I have 3 possible ways of choosing the central processing unit. I can choose either X, Y, or Z. The same outcomes exist when I choose B as the first step. Then for the C also, we have 3 possible outcomes, X, Y, or Z. And for D, we also have X, Y, or Z as the outcome of the second step. So in order to count the total possible combinations of input-output unit and central processing unit, we start from the top of the tree here when we have a combination A and X. So that's one possible combination. A as the input-output unit, and X as a central processing unit. Then A and Y is the second one. A and Z is the third one. B and X first. B and Y, B and Z. Then C and X, C and Y, C and Z. And finally D and X, D and Y, and D and Z. So if you count all of these possible ways, you will find out that we have 12 different outcomes for doing the first and second steps combined. So we have 12 different pairs of input-output unit with a central processing unit, right? So this example illustrates the concept of multiplication rule that we define in the next slide. Okay, so here is the multiplication rule. If an operation consists of k steps and the first step can be performed in n sub 1 ways, then the second step can be done in n2 ways, regardless of how the first step was performed, and all the way to the kth step. The kth step can be performed in n sub k ways, regardless of how the preceding steps were performed. Then the entire operation can be performed in these ways, in n1 times n2 times n3 all the way to nk ways, which is the product of I from 1 to k different ways. So let's see an example. Consider example 922, which we find the total number of possible personal identification numbers, PIN numbers. You know that typically a PIN number is a sequence of 4 symbols chosen from the 26 letters of the English alphabet and the 10 digits from 0 to 9. And obviously the repetition is allowed. For example, you can have a PIN number of 111. So the question here is, how many different pins are possible? To solve this question, we are going to use Theorem 921, the multiplication rule. Consider choosing a pin as a 4-step process. In the first step, we need to choose the first symbol. In the second step, we need to choose the second symbol. For the third step, we choose the third one, and in the fourth step, we choose the fourth symbol. You know, there are a fixed number of ways to perform each one of these steps. How many steps, how many different ways we can find the first symbol? 36 steps. 36 ways. Why? Because we can either choose a letter, which are or a digit, right? We have 26 letters and 10 digits, so we have a total of 36 different ways of choosing the first symbol. In a similar way, you can say we have 36 ways to choose to do the second step and third step and fourth step. Then we use the multiplication rule to conclude that there are 36 times 36 times 36 times 36, which is 36 to the power 4, which is 1,679,616 different pins in total. So this figure illustrates the process. We have first step for filling the first letter, the first place of the pin. Then for the second letter of the pin, we have again 36 choices among all of these possible choices, And then for the third step, we have also 36 choice. For the fourth step, we have 36 choice too. So in total, regarding the multiplication rule, we have 36 to the power 4, which is 1,679,616 different pins. Okay, so let's see another example. Example 924, which again wants us to find the number of pins. This time, when repetition is not allowed in choosing a pin. For example, having a pin of 1111 is not allowed, or having a pin of 2334 is not allowed because 3 is repeated more than once. The question here is how many different pins are there, and the second part of this question is if all pins are equally likely, then what's the probability that the pin is chosen at random contains no repeated symbols, correct? So in order to find the answer for part A, we have to think of creating a pin as a 4-step operation. In the first step, you have to choose the first symbol, then you choose the second, then you choose the third, then you choose the fourth. There are 36 ways to choose the first symbol. That's obvious, right? Because when you are choosing the first symbol, there's no restriction. But when you are choosing the second symbol, you have only 35 ways. Why? Because the first symbol cannot be used again. So out of a pool of 36 different symbols, we cannot choose one of them because one of them is chosen for the first step and repetition is not allowed. So we have only 35 valid choices in the second step, and in the third step we have even less. We have 34 ways to choose the third one because the first two symbols cannot be reused, and the last step has 33 different ways to do it. Why? Because the first three symbols cannot be reused, so we have the total of 36 symbols, and 3 of them cannot be reused based on the restriction that the problem has placed. So the last step, which is the fourth step, can be done in 33 ways. So based on the multiplication rule, we can create a pin with no repetition in 36 times 35 times 34 times 33 different ways, which is equal to 1,430,720 different ways. So we have this much different pins with no repeated symbols. In part B, we are asked to find the probability of choosing a pin with no repeated symbol. So we need to find the ratio of 1,413,720 different pins with no repetition divided by 1,679,616 I'm sorry, 1,679,616 different pins which may have repeated symbols, right? So when you divide these two numbers, you get 0.84 approximately. So the chance of having a pin with no repeated symbol is 84%. The next topic is about permutations. A permutation is defined as follows. A permutation of a set of objects is an ordering of those objects in a row. For example, if you have a set of elements A, B, and C, we have 6 different permutations: ABC, ACB, CBA, BAC, BCA, and CAB. So we have 6 different ways of ordering the elements A, B, and C in a row. So in general, if you have n different elements in a set, the question is how many permutations does this set have? And to find the answer, we can imagine forming a permutation as an n-step operation. In the first step, you're going to choose the element who comes first. In the second step, you need to choose an element to write second, and the last step, which is the nth step, is to choose an element to write in the last place, which is the nth place. So in order to find the total number of permutations, we have to find out in how many ways we can do each of these n steps, right? So any element of the set can be chosen in the first step. So we have n ways to perform step number 1 because there is no restriction for choosing the first element. But after you choose the first element, that element cannot be chosen in any of the next steps. So for step number 2, you cannot choose that element that is chosen in step 1, so you have only n-1 different ways to perform step number 2, and then when you go to the next step, the number of ways to perform the next step becomes 1 less than the number of ways that you can do the current step, correct? So in each step, the number of ways to perform that step becomes 1 less than the previous step. So at the last point, at the last step, you have n-1 elements chosen, and you are left with only 1 element in the set. So the number of ways to choose the last element is only 1, because you are going to choose 1 element out of the 1 element that is left. So based on the multiplication rule, we need to multiply the number of ways that we can do each of these steps, step number 1 all the way to step number n. So the number of total permutation would be n times n-1 times n-2 all the way to 2 times 1, which is equal to n factorial. Okay, so let's see an example 9 to 8, which is about counting the number of permutations of letters in a word. For example, the question is how many ways can the letters in the word computer be arranged in a row? The answer is there are 8 different letters in word computer, so these 8 letters are distinct, and as a result the number of ways that you can arrange these letters is equal to the number of permutations of a set containing all of these 8 letters. So based on what we said, what we just said, we have a total of 8 factorial or 40,320 different ways of writing the letters of computer in a row. Okay, so we calculated the number of permutations of a set of size n using multiplication rule, and then we said there are n factorial different permutations for the elements of a set of size n. Now here we talk about the extended form of this permutation. We say given a set like A, B, and C with 3 different elements, there are 6 different ways to select 2 letters from this set and write them in order. How? For example, we can write A, then B. We can remove C because we only need 2 letters. Then we can write AC, BA, BC, CA, and CB. There is no other way of writing 2 letters out of these 3 letters, A, B, and C, in order. So as you see, we write A, B, and then we write BA because order matters in a permutation. So each such ordering of 2 elements of the set A, B, and C is called a 2 permutation of A, B, and C. So when we say 2 permutation means you need to first choose 2 elements from this set and then write all the permutations of that 2 elements that is chosen out of the 3 possible elements of the set. So in general, we have a definition in the following way. We say an R permutation of a set of size n is an ordered selection of R elements taken from the set of n elements. So it should be ordered selection, right? It's not only a selection of R elements, it is an ordered selection. Why? Because it's an R permutation. The number of R permutations of a set of n elements is denoted by this symbol, P of n and R. Means R permutations of a set of size n. Now we have a theorem, a very useful theorem, Theorem 923, which basically says if n and R are 2 integers and R is between 1 and n inclusive, then the number of R permutations of a set of size n is given by the formula of P of n and R equal to n times n minus 1 times n minus 2 all the way to n minus R plus 1. Or equivalently, you can write it in the form of factorials. You can say it's equal to n factorial divided by n minus R factorial. And in order to prove this theorem, you can again use multiplication rule. You can say we have a pool of available elements x1, x2 all the way to xn at the beginning, and then you need to choose all of these n elements and make them ordered. You have to order them. So for the first position you have n different choices, but for the second position you have only n minus 1 choices because you cannot reuse the element chosen in the first step. In the third position you have one less number of choices. You have n minus 2 choices all the way to position number R, where you have n minus R minus 1 different choices, or n minus r plus 1 choices for the last position. So using the multiplication rule, you can multiply n by n minus 1 by n minus 2 all the way to n minus r minus 1 to find the total number of ways that we can find an ordered selection of r elements out of these n possible elements. As an example of R permutation, consider example 9 to 11. The question is, how many different ways can 3 of the letters of the word bytes can be chosen and written in a row? So the first thing you need to do is to count the number of letters in the word bytes. We have 5 distinct letters in this word. And then, since we are going to find the 3 permutations, the total number of 3 permutations of these 5 letters, we need to find out what the value of P of 5 and 3 is, because P of 5 and 3 is the total number of 3 permutations of a set of size 5, correct? So it should be equal to 5 factorial divided by 5 minus 3 factorial, which is equal to 60. And then in part B, the question is, how many different ways can this be done if the first letter must be B? That must be the letter B. So as you see in this figure, the first position is occupied by B, so there is only one way of filling position 1, because we are forced by the question to fill position 1 by letter B. So we only have 2 available positions, position number 2, position number 3. The first position, the second position, position number 2, can be filled by any of the 4 remaining letters of word bytes, because B is already positioned on the first position. So we only have 4 available letters that can occupy the second position. And after choosing that letter for position number 2, we are left with only 3 letters that can fill position number 3. So we have 4 different possible ways of filling position number 2 and 3 possible ways to fill position number 3. So we have a total of 12 different permutations for part B. But you can also solve this problem in a different way using P of 4 and 2. How? You can say the first position is occupied, so we only have 2 positions and 4 available letters. So we are going to find the 2 permutations of these 4 letters for the remaining 2 positions, correct? So in order to find the number of 2 permutations in a set of 4 elements, you need to calculate P of 4 and 2. If you do this, you'll get the same answer. You'll get 12. So in previous slide, we defined R permutation of a set of size n, and we calculated the number of R permutations of a set of size n using multiplication rule. Now here, we define the R combination of that set of size n in the following way. We say the number of subsets of size R is called the R combinations of a set of size n, and the symbol is exactly what we defined in the previous chapters for n choose R. That's the symbol that we use, and this symbol is equal to P of n and R, the number of R permutations of a set of size n, divided by R factorial, where n and R are non-negative integers and R is not greater than n. So You can also find out this, find this, ratio for the value of n choose r, which is n factorial divided by r factorial times n minus r factorial, which we can prove that this is exactly equal to this one. So in order to prove that n choose r is equal to this quotient, we basically consider the process of forming the R permutations for a set of size n as a two-step process. In the first step, we need to choose R elements in a set of n elements. And in the second step, you need to choose the permutation of these R elements that is chosen in step 1. And if you do these two steps sequentially, then you can form an R permutation for a set of size n. So based on the multiplication rule, if I find the number of ways that we can do a step 1 and the number of ways that we can do a step 2, then we can find the number of total R permutations of a set of size n by just multiplying the number of ways that we obtained for steps 1 and 2. If you look at step 1, when we are going to choose R elements out of a set of n elements, then the number of ways is equal to n choose R. That's just the definition of n choose R. And in the second step, we just need to find the number of permutations for a set of R elements that are chosen in the previous step. This step can be done in R factorial number of different ways. So based on the multiplication rule, there are a total of R factorial times n choose R permutations of R elements chosen from a set of n different elements, correct? So P of n and R, which is the number of R permutations of a set of size n, is equal to R factorial times n choose R. So if you divide this equation by R factorial, you'll get n factorial equal to P of n and R divided by R factorial. And if you replace P of n and R with its equivalent value that we obtained in previous slides, you'll reach to this quotient. In the numerator we have n factorial, and in the denominator we have R factorial n minus R factorial. All right, so we introduced the multiplication rule in the previous slides. Here I'm going to introduce the addition rule. Consider you have n different sets that are mutually disjoint, sets A1, A2, all the way to AN. Then we claim that the union of all of these sets has this number of elements, n of A1 plus n of A2 all the way to n of AN, which is the summation of I from 1 to n of cardinality of AI. So the addition rule looks very obvious because, for example, if you have 5 apples and then you have 3 oranges, you have a total of 8 different fruits. That's what the addition rule says. But when you extend the addition rule to the inclusion-exclusion rule, it gets a little bit more complicated. The inclusion-exclusion rule considers the following situation. Look at this Venn diagram. You have 2 sets, A and B, that are not necessarily disjoint. They may share an area of A intersection with B, and obviously the shaded area represents union of A and B, correct? So I'm going to prove that the number of elements in in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So I'm going to prove this equation, correct? In order to prove this equation, let's start with n of A. Consider n of A as the cardinality of A. So n of A counts two different kinds of elements. N of A counts all the elements that are in A but not in B, and the elements that are in A and B, in both A and B. Similarly, n of B, the cardinality of B, counts two different class of elements. The elements that are in B but not in A, which are in this region, and again, the elements that are both in A and B, correct? So let me draw this with the blue line. So n of B covers this area and this area, correct? The intersection of A and B and the area that is only in B, not in A, correct? So if we add n of A and n of B, what happens is that we count the elements in this region and in this region once, but we count the number of elements in the intersection of A and B twice, correct? So we need to subtract the number of elements that are in both A and B from the summation of n of A and n of B, because we have counted the number of elements in A and A intersection B twice. In summary, when the two numbers n of A and n of B are added, then the elements that are in both A and B are counted twice, and to get the accurate count of the elements in A union B, it is necessary to subtract the number of elements that are in both A and B, and because there are the elements in A are A intersection with B, then n of A union B is equal to n of A plus n of B minus n of intersection of A and B, because the elements in A intersection with B are counted twice in this summation, so we have to subtract it once so that we count every element in union of A and B exactly once. So you can extend the inclusion-exclusion rule to three different sets, A, B, and C, and we can have this equation right here. We can say n of A union B union C is equal to n of A plus n of B plus n of C minus n of intersection of A and B minus n of intersection of A and C minus n of intersection of B and C plus the cardinality of intersection of A, B, and C. So I'm not going through the details of this equation, but you can look into the book to get more details about the last equation that we presented here. Okay, so the last subject that we talk about in chapter 9 is the pigeonhole principle. For example, consider a case where you have 5 pigeons and 4 pigeonholes in this picture. The pigeonhole principle claims that there should be at least one pigeonhole that contains 2 pigeons. In fact, each pigeon chooses one pigeonhole, correct? So in this case, since the number of pigeons are more than the number of pigeonholes, so there should be one pigeonhole that more than two pigeons select. So in this case, pigeonhole number 3 has two different pigeons, but the other pigeonholes may have one or even zero number of pigeons, but we can certainly claim that there is one pigeonhole that contains more than one pigeons. Why? Because we have more pigeons than pigeonholes. So this pigeonhole principle uh, looks very obvious, but when we extend it to a generalized form of pigeonhole principle, it may be a little bit less obvious. So in order to formally define pigeonhole principle, we need to use the concept of functions and one-to-one functions. We say a function from one finite set to a smaller finite set cannot be one-to-one. Why? Consider this example. The domain of this function is the set of pigeons, and the codomain is the set of all pigeonholes. So since we have 5 elements in the domain and 4 elements in the codomain, it's impossible to have a one-to-one function, and we should have at least 2 elements of the domain, like elements number 1 and 4, pigeon number 1 and 4, that they both go into the same pigeonhole, that they both are mapped into one element in the codomain. That's why it is not possible to have a one-to-one function from a finite set to a smaller finite set. In order to apply the pigeonhole principle, we can consider these two examples. In a group of 13 people, there must be at least 2 persons who were born in the same month. Why? Because we have only 12 months in a year, and 12 is less than 13. In this example, the 13 people are like 13 pigeons, and the 12 months of a year are like the 12 pigeonholes that we have. So we can for sure say there are at least 2 people, 2 pigeons who have this, who are born in the same month, who go to the same pigeonhole. And then the next example is this: among the residents of New York City, there must be at least 2 people with the same number of hairs on their heads. Why? Because we have at most 300,000 hairs in someone's head, sorry. And the population of New York City is about 5 million. So we have 5 million different people in New York City, but there are only 300,000 hairs on someone's head. Since 300,000 is less than 5 million, so we can say for sure that there are 2 people in New York City who have the same number of hairs on their head. Okay, so let's see the generalized pigeonhole principle. Consider we have 9 different pigeons and 4 pigeonholes, and again, each pigeon can only reside in one pigeonhole, correct? So what generalized pigeonhole principle says is that there should be a pigeonhole in which there are more than 2 pigeons. Why? Because 9 is greater than twice the number of pigeonholes. So there should be one pigeonhole with more than 2 pigeons. If you want to define it in a more formal way, you need to use the definition of functions. So you can say for any function from a finite set X, that's a domain of the function, with n elements, to a finite set Y, which is a codomain with m elements, and for any positive integer k, if n is greater than k times m, then there is some y in the codomain, there is some element in the codomain such that y is the image of at least k plus one distinct elements in the domain. So here is the representation of the same pigeonhole principle example using functions. The domain, which is the set of pigeons, has 9 elements, which is more than twice as the number of pigeonholes or the number of elements in the codomain. And as a result, you see that there is one element like 3 in the codomain that is the image of more than 2 elements in the domain. So basically, if you consider k equal to 1 in the generalized pigeonhole principle, you'll get the actual pigeonhole principle, the original pigeonhole principle that we defined in previous slide. Why? Because here we have k, if k is equal to m, if k is equal to 1, then if n is greater than m here, then there is at least 1 plus 1, which is 2 distinct elements of x. So basically, we'll get the original pigeonhole principle by letting k equal to 1 in the generalized pigeonhole principle. Let's see an example of generalized pigeonhole principle. Let's assume that the question is this: show how the generalized pigeonhole principle implies that a group of 85 people in a group of 85 people, at least 4 must have the same last initial. So we are going to show that in a group of 85 people, 4 of them at least have the same last initial. How can you show that? We say, in this example, the 85 peoples are the 85 pigeons, right? And how many pigeonholes do we have? We have 26 possible last initial for their names, so we have 26 possible pigeonholes. And since 85 is greater than 3 times 26, which is 78, so 85 is greater than 78, which is 3 times 26. According to generalized pigeonhole principle, there are at least 3 plus 1, which is 4 people with the same last initial.